All right, so here's your lesson for today on modeling with mathematics. This one's a very authentic modeling situation where first we're learning lessons about different types of functions. Now we're going to apply it and see in a real world situation what kind of math model could we use. So number one says sketch a graph to model each of the following situations and think about the shape of the graph and whether it should be a continuous line or not. So I'm going to look at each situation. I want you to know before we start sketching or do anything else, this is connected to the back of the sheet or the second sheet. So we need both the first and second sheet together at the same time to be able to work at it. But let's just look at each situation first. So the first situation is a candle. Each hour, a candle burns down the same amount. And that idea of the same amount is going to be important to know how we're going to model it. And the x-axis is going to be the number of hours that have elapsed, and the y is going to be the height of the candle in inches. So let's just start there, and then we'll look at the other situations. So a candle that burns down the same amount each hour, and which one could model it? So what things do we know what this graph will look like? Well, one thing we need to know is this going to be a continuous line or not? And as a candle is melting, that is a continuous situation. So it doesn't stop melting in the middle of it and then pick up again like a minute later. It's continuously melting down until there is no candle. So it is a continuous situation. But what kind of math model can model a candle burning down at the same amount? And another one I'm going to say is a constant rate. So let's look at the second page and think which one could model something that looks like that. Then we'll go back and actually graph it. So we have on the second page 4 equations that it could model. And so we want to be able to understand each one and be able to understand, no, it can't be this one or it could be that one and so on as I look at it. So the first one is y equals 300 over x. So that is a rational function. And in this situation, this one does not have continuity when x equals 0. Now in our modeling situation, x is the number of hours. So x can equal 0. That's the initial height of the candle. So it can't be undefined. So for our situation, it cannot be the first equation. That's not going to model what it looks like because at x equals 0, it's undefined. Okay, the next one. 12 subtract 0.5x. What type of equation is this? Well, this one's linear, so I'm going to write down what this is actually as I go along here. So this one's rational. This one is linear. Now, what do we know about this line? Well, 12 is the y-intercept, but in a real situation, 12 is the initial amount. And then subtract 0.5x, this is the rate. And what do we know about the rate? Is it increasing or decreasing? So because it's negative in front, it's decreasing, and it's decreasing by the same amount. So in our situation, we have a candle, and it's decreasing, it's melting at a constant rate over time. Could this model a candle melting, where you start at a certain height, and then it constantly melts at the same rate until there is no candle? So that one definitely has a possibility. Here, 30 plus 20x. Again, it's linear, and again, why do I know? Because the exponent on x is 1 that you don't see. But what's different about this one is we do have an initial amount, the y-intercept, but the second part, 20x, what do you notice about the rate? The rate is constant, but it's positive. That means it's increasing over time. In our candle that's melting, obviously the height is not increasing over time, but decreasing. So that one, it does not match your situation. And then we have an exponential model where something is growing exponentially or maybe decreasing exponentially. So that base would tell us in terms of that. So as a candle melts at a constant rate, is that increasing or decreasing exponentially with an exponent there, with the variable and exponent? So that one also does not fit a candle because of what we're doing, because it is a constant rate, or it's decreasing at the same amount over time, and exponential would be increasing or decreasing not at the same amount each time. All right, so which one's going to match our situation? So I want you to notice that this one here is going to match it. So A, that situation A is the candle melting. So I'm going to come back here. I'm going to write down the equation, which is 12 subtract 0.5x. And then I'm going to graph this one. So the y-axis is going to represent the height. So obviously, what number do I must go to for the height? And that is 12. So I'm going to count by 2's, I think. So it's going to go up there. So I know it starts here. And then on the x-axis is going to show the time elapsed. Now, one thing it'd be good to know is what is the x-intercept? In other words, what does the x-intercept represent in this case for this model? And the answer is it represents when the candle is no more. And so when the candle is at a height of 0, that means there is no candle. And I'd like to know the x. I'd like to know what time that takes place. So how would I solve this? So personally, I would add 0.5x. And then to get x by itself, I divide by 0.5. I don't care. You can use Desmos if you want to, or a calculator. But 12 divided by a half. That answer is going to be 24. So 12 divided by 0.5. You multiply times the reciprocal. If you do it without a calculator, it'd be 12 times 2. 24 is my y. So what I'm going to do across here is I'm going to get to 24. So again, I'm going to count by 2's, I think. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 24 is right there, right at the end. So again, I'm counting by 2's. I'm just going to draw a line that connects those two together. And it does not go on forever, modeling. We don't have negative time, and we have no height that goes into negative numbers. So it's just a line segment that goes and connects it from there to there. Now, let's go to the second page and answer the questions to do with that situation. So in 3A, it asks us a question about it. We actually already answered it. How long will the candle last before it burns out completely? Well, we'll show our work again, but we take that equation and make it equal to 0, because when there is no height, the candle is no more. We added 0.5x and then divided by 0.5, and we got our answer. So the answer was 24 hours until the candle burns away. All right, let's look at the next situation. B, a letter. People send letters anymore. When sending a letter, you pay quite a lot for letters weighing up to an ounce. You then pay a smaller fixed amount for each additional ounce or part of an ounce. So in other words, up to 1 ounce, it costs the same. So whether it's half an ounce or just the littlest amount, it would cost you the same amount up to an ounce. And then you go to the next ounce. So if it's over 1 or anything between 1 and 2 ounces, it would then cost the same amount as 2 ounces. So 1.8, that's 2. 1.1, that's 2. So they always round up to the nearest ounce in terms of the cost. So it says you pay a smaller. Now again, I'm looking at the word fixed amount for each additional ounce. So that's important, fixed amount. So now let's go to the second page and think which one could be the one I'm looking at. So we have a letter situation. So here we have a rational function again. I want you to get an understanding as you plug in numbers for x, so 1 ounce, 2 ounces, and so on, I want you to know the answer is actually getting smaller. This is a decreasing function. So if I plugged in 10 ounces here, that would actually cost less than if I plugged in 1 ounce. That does not make sense. This does not model my situation. If I look here to the far right, we have an exponential situation, which goes against the idea of a fixed amount for each additional ounce as it grows or decreases exponentially. I want you to notice the base of the exponential is a fraction, a number less than 1. And because it's that, it's actually decreasing. If you are confused by these models a little bit, you can also go to Desmos, type it in to get a picture of it and see that. Now, this one's going to be a little confusing in terms of the picture. So we have an equation. This one seems to match it kind of, because what I notice is this. It's linear, which is that idea of a fixed amount being linear. And then the second part is it's positive. So the rate is positive 20 that we're looking at. That means this linear is growing over time. And of all of these situations, this is the only model that's actually growing, increasing as a model. So this is the one that's going to model B, but we have to be careful how we graph it. So let's come back here. So we got y equals 30 plus 20x. And so we're going to graph this, but have an understanding of it. So first of all, we're going to graph it in terms of 1 ounce, 2 ounces, 3 ounces, 4 ounces. I think that's fine to get up to 4 ounces in terms of it. And then what is the y-axis? What is it going to look like? Now, this is not going to look like a line the way that would look like if you type in a Desmos. And the reason is, for 1 ounce, if I plug in 1, 30 plus 20 is 50. So I know originally this answer is 50. Let's go by tens. So 1, 2, 3, 4. So there's 50. So at 1, the answer is 50. But the thing is, if it was half an ounce or quarter of an ounce, it would still be 50. Now, exactly at 0, there'd be a hole. And the reason at 0 there'd be a hole, well, something weighed 0 ounces, it does not exist, it won't be mailed. So there is no value to put on the graph at 0. But anything from 0 to 1 costs how much? 50. So if I want to know the next amount to put in, you plug in 2. And so if I plug in 2, 40 plus 30, the next amount is 70. So I have to go up to 70. Now, at 70, anything above 1 all the way up to 2 is going to cost 70. Now notice I have to put a hole, and I tried to line it up without graph paper, a hole over this, because at 1 ounce the cost is 50, not 70. But anything after 1 ounce it costs $70. So notice the picture of what it's going to look like. It's going to look like a greatest integer function in terms of what you did when you did the lesson on parent graphs. Next, plug in 3. So 20 times 3 is 60, plus 30 is 90. But notice we're going up by 20 each time. So if we can understand the rate is going up by 20, then we can have a good picture. Let's see if I can draw this a little more accurately. So anything up to 3 is going to cost $90. Man, it feels like I'm not lining it up when I look at the camera, but I'm trying my best. And then the next one, add 20 again, then you get 110. And so anything up to 4 ounces there, so anything from 3 to 4 ounces is going to cost 110. So there's a picture, a model of this situation of sending letters. Now, if I would connect these solid points together, it would draw the line 30 plus 20x. But our situation, our real world situation, means that we're not connecting it as a solid line. So when I read it carefully, up to an ounce, 1 to 2 ounces, 2 to 3 ounces, and so on, we need to see these steps that are created in there. And try to be accurate as best as I am. I'm trying to line it up, and I'm noticing that I'm a little skewed here, trying to line it up over 2 or 3 or 4 and so on. All right, part C. So, let me go back and answer the question they have to do with a letter. So it says, how much will a letter cost a letter weighing 8 ounces? So if we take our model, y equals 30 plus 20x, and then plug in 8 ounces, that's 160 plus 90, 160 plus 30, so it's 190. Remember, this is in, what is it? X is in cents. That's 190 cents. So it will cost $1.90 to send a letter weighing 8 ounces. There he goes, OZ. That's weighing. All right, 2 more, and then we're done with the lesson. C. So in part C, it says, a group of people rent a bus for a day. The total cost of the bus is shared equally among the passengers. And then we have X being the number of passengers and Y being the cost for each passenger in dollars. So to understand this modeling, if there's only 1 person going, it's going to cost a lot. If there's 10 people going and you share the cost, then the cost per person is going to go down. So this one is going to decrease over time. So we have to look at each one in terms of understanding that. So we have 2 that are decreasing that are left. One is irrational, and the other one one is irrational, and the other one is exponential in terms of what we're looking at. So which one's going to model our situation? And so if X represents the number of people and Y represents the cost, which one would be a better model in this situation? So if I plugged in 1 or 2 or 3, which one's going to be able to be the one that models it in a better situation? Because they both, in a sense, are modeling in a decreasing situation over time of the 2 that are left. But the one that's a better model as we go through it is actually this one, which is 300 over X. So if one person goes, then it's going to cost $300. But if 2 people go, and I divide by 2, then they're going to share the cost. So now 300 divided by 2 is 150. If 10 people go, then 300 divided by 10, now they're sharing the cost, and they each only pay $10 each. So this is the one that's going to match with C. If I try to do substitution in terms of understanding this situation, if one person goes or if 2 people go, you're not going to get that same situation where you're splitting the cost in half when you try it, or splitting the cost equally among 10 people and so on. This is the one that matches that situation with the bus. So we're going to go back, and we're going to graph that. So it's 300 divided by X. So let's write that here. Y equals 300 divided by X. How am I going to graph it as a real-world situation? So I'm going to actually go to 10 people just to graph. And it could go on. You could have 300 people, and then it's 300 divided by 300. And each person would pay $1. How many people do you think would fit on a bus? What would be like more of a real-world situation? Well, let's say 30, because 30 would seem to make sense on a bus more than 10. 10, you'd think you'd have a lot of empty seats, and 30 goes into it evenly. So let's just go to 30. So we're going to go to 30. I'm going to count by 5. So 5, 10, 15, 20, 25, 30. So X represents the number of passengers. 0, there's going to be nothing. So if no one goes, there is no cost. And we have to go by whole numbers too when we do this kind of work. So if I understand if one person goes, it's going to go all the way up to 300. So if I think of 300 as way up here, one person would be all the way up here to 300. But I'm going to pick nicer numbers. Like if 5 goes into it, what's the number? And by the way, all the way here 30, the bottom value would be 10. But I'm going to count here by what would be a good value to count by? 50s. So 50, 100, 150, 200, 250. That seems like it would fit nicely on the graph. So I'm just going to estimate 1 right here at the beginning would cost 300. Now, how much would it cost for 5 in terms of what's happening, or for 2 and so on? So if I look at 2, it would be 150. So if I think of where 2 is, it's 150. Now notice I'm not going to connect these points together. That's because we can't have 1.5 people or 1.25 people on this bus. They're just going to be whole numbers. So in this situation, notice that this was not continuous. As you can look off the graph, this will also be not continuous because we need whole numbers here. So 1.5 does not work. 1.25 doesn't work. So we're not going to connect them. Just each whole number is going to be a point on the graph. And I'm not going to do every point from here to there. So 5, 300 divided by 5, take my calculator, right? That's 60, right? I shouldn't need a calculator for that. 60. If 10 people go, that's 30. If 15 people go, see, I'm doubting myself here. So I'm going to use my calculator. 300 divided by 50, may not even go evenly. 20, so at 15 it's 20. At 20, this one's the one that's not going to be an even number. So at, oh no, 20 is good, that's 15, I should know that, right? So you can see at each one it's decreasing, and then at 30 it's going to be 10. So we can show it decreasing from here. So again, why am I not connecting these points? Is because you can't have half a person in between. Now I could even have more points here, and as you see, for each person that you put on, you could actually have a point on our graph, and you can see it decreasing. Now, you'll never have a situation where it will cost $0. It will always cost something. So even if you had 1,000,000 people on that bus, which would be impossible, you'd still have like a part of a penny that each person would have to pay or something like that. So it'd be impossible to get to zero cost and zero. So these are actually asymptotes along the x and along the y-axis. Let's see what the question is for part C. In part C, it says, if 20 people go on the coach trip, how many people have to pay? So we already did this one in a lot of ways, right? So if I divide by 20, we said the answer was 15. So if 20 people go on the trip, it will cost how much each? Oops, right here, $15 each, right? All right, one more to go. So obviously the last situation would have to go with D, right? So here's this exponential situation. So let's go back to see why that exponential situation fits. So it's 2,000 times 0.5 to the x. So I'm going to type that in, or type it in. 2,000 times 0.5 to the x. So there's my equation. Let me get it up there. There it is. So you have a car that loses about half of its value each year. Notice that 0.5 there, right? Half the value each year, 0.5. And the time that has elapsed in years, and then y is the value of the car. So for this situation, you do have an initial amount for the car. So how much did the car cost initially? Plug in 0, and you can see the car cost $2,000. Pretty cheap car to begin with. I will count by, I don't know, 500s. So right here at 2,000, it starts. Now notice this will be continuous because it's time. So it's decreasing with time. So you can have a day, an hour, a second, a millisecond. Like it's going to be continuous, all this. So this one is continuous. There's no holes or breaks or anything like that. And so as you go along, let's just go 1 year at a time. So for 0, for 1 year, how much would it cost? So if you plug in 1, I'm going to use my calculator. So if I go 2,000 times 0.5 to the 1, or just times 0.5, I get 1,000. So it loses half its value. I shouldn't even need a calculator for that. And then at 2, the cost would be 500. And at 3, the cost would be 250. And at 4, it would be 125. And this one is continuous, and you can go here. There will be never a time where the cost would be 0. So it keeps losing half its value. It's impossible to get the answer 0. So you could get down to a penny, whatever time that is, but it will never be 0. So this is continuous, but there is an asymptote over 0, or it will never equal 0. All right, let's answer the question. Part D. How much will my car be worth after 2 years? So that one's pretty simple. So after 2 years, plug in 2 into there, and we already figured this out on our graph. After 2 years, the cost would be $500. We already did it on our graph. Let's write a nice simple sentence. So after 2 years, the car will be worth $500. Awesome. All right, Mr. G Math, over and out. Thank you for doing your work, and we'll do another modeling one tomorrow. All right, till next time.